Hello and welcome to our next video on topic 6, inference with estimation. Here in part 5 we're going to talk about how to determine sample sizes in a few different settings, and then we'll do a short postscript conversation on what we really mean when we talk about 95% confidence intervals or 90% confidence intervals. So let's start by looking at sample size calculations for the situation when we're looking at population means. So if we have a given level of confidence, such as 95% or 99%, the sample size that we have is going to determine the margin of error, as we've seen before, and the interval estimate, the width and the precision of the estimate. Now, what if we want to go in reverse? So we've already looked at this first scenario, and now we want to go in the reverse direction. In other words, what sample size would you need in order to have some desired level of confidence or some margin of error? So we're going in the reverse direction that we've gone up. So let's start with a case where we're computing sample sizes for population means. In that particular case, we saw before that our margin of error is composed of two pieces. We have here our confidence multiplier, and then we have our standard deviation of the sampling distribution of sample means. Now, we could actually take this expression right here, and we could simply solve for n. This is an expression with multiple variables. We have an n down here, so we could manipulate this equation using several steps, and we could solve for n. We're not going to do that here in this video because it's not really the focus of what we want to learn. But let's just suppose we take out our algebra tools and we crank through that, and we get this. Using algebra, we can solve for n from that previous expression, and we get that the sample size is equal to our confidence multiplier multiplied by the population standard deviation divided by the margin of error, and then that whole quantity is squared. Now, when you do this, you're most likely, in most cases, you're going to get some kind of number with a decimal part. But of course, a sample size needs to be an integer. So whenever we need to, we're simply just going to round up to the very next highest integer so that we don't end up with weird results like a sample size of 12.3. So just keep that in mind. Also keep in mind that for this to work, you're going to need to know the population standard deviation, sigma. So let's go back and revisit that department store example that we talked about in a previous video, where you're randomly selecting customers to learn more about how much they spend at your store in a given week. Since you've been doing that for years, as we talked about before, we know the standard deviation sigma is 20. And so let's suppose we want a margin of error of no more than $5 at a 95% confidence interval. What should our sample size be? So we want to be 95% confident, and we want our margin of error to be no more than $5. So here's what the calculations are going to look like. Here's our expression for n. We're just going to fill in everything that we know. Because we're looking at a 95% confidence interval, we'll estimate z star to be 1.96. Sometimes we've used 2, but in this case we're going to shift to 1.96. Also, sigma is 20. That's given to us in the original problem up here. So sigma is 20, and n is our margin of error that's desired. That's $5. So if you compute just the inside part of this, you'll get 7.84. And then when you square that, you get 61.4656. Of course, because this is not an integer, and to be safe and conservative, even though this is less than 5, we're going to go ahead and round up to 62 to guarantee that we get the margin of error no more than 5 at that particular confidence level. So if you're in the department store running this survey and you had these constraints in front of you, you would need to have at least 62 people take that survey, 62 random people to take that survey in order to get these criteria matched. Now, what if you went to your manager and said, well, $5 is too much of an error. I really want it to be much tighter than that. And your manager said, let's go for a margin of error of no more than $1. Will n get larger or smaller? If you think about that for a second, we've talked about this in a previous video. What's going to happen to our interval and our margin of error as our sample size changes? If you think back to the expressions that we've been working with, typically the larger the sample size, the smaller the margin of error. So if you want a smaller margin of error, then you're going to need a larger sample size, and vice versa. So in this case, as before, we saw the margin of error was 5, and we needed a sample size of 62. If we replace this margin of error 5 with the new value 1 that we want, your expression is the same everywhere else except here, but now this number gets a lot larger, and therefore when you square it, it gets much, much larger, and so your sample size is huge. So if you want a very small margin of error, if you want to be 95% confident, and you want to be within $1 instead of 5, then your sample size is going to get much larger. And so you can go back to your manager and say, whoa, wait a minute, that we would need a sample size that's way too large, so we have to decide what trade-off we want to be able to make here. Now this was a scenario where we knew the standard deviation sigma because of many years of data. What if we don't know the population standard deviation? In this case, there is what we call the range rule of thumb. So it's a rule of thumb related to the range of the data. Recall from a much earlier topic, the range of a data set is its max minus its min. So that's our range. And the rule of thumb says that if you don't know what the standard deviation is for the population, you can approximate it as 1/4 of this number here. So therefore, your standard deviation will approximately be equal to the max minus the min, all divided by 4. So that's a quick rule of thumb that you can use if you don't know the population standard deviation. Now let's go ahead and shift over to sample size calculations for when you're calculating population proportions. So for a 95% confidence interval, we're going to use the following guide. So this is the only confidence interval for which we're going to provide this guide. Others would require different formulas, but for now, because the 95% confidence interval is the most common one, we'll stick to this just for the sake of keeping things simple. In that case, we would say that the sample size is equal to 1 divided by the margin of error squared. Now you can go into the reading and you can see where they got that and how they derive this from more complex expressions. But this is a relatively straightforward and easy expression or formula to use if you're working with a 95% confidence interval. Remember, our margin of error, m for a proportion, is going to be a decimal value between 0 and 1. So think about polling at election time. You often see polls on CNN or Fox News or other news stations that poll people about approval ratings or what candidate they're favoring to vote for in the upcoming election. And you typically see margin of errors of plus or minus 0.03. If you were looking for a margin of plus or minus 0.03 and you're constructing a 95% confidence interval, then the sample size n that you need is going to be 1 over m squared or 1 over 0.03 squared, and that's about 1,112 people. So if you look carefully at the information that's given to you on these news stations when they report polls, you'll sometimes see a sample size given to you, and if you see a 0.03 margin of error, then you will often see something very close to a sample size of about 1,000 people. So about 1,000 people had to be randomly selected to take that poll in order to construct a 95% confidence interval with this margin of error, 0.03. It's very rare that they will report a 95% confidence interval as the one they're actually using. You don't usually see that. However, that's pretty standard from what I understand. And so when you see polls, this is probably what they're reporting. So in other words, if you see a news station report that 51% support the Democratic candidate for an office with a margin of error of plus or minus 0.03, it's very likely that they're computing a 95% confidence interval. And so what they're really reporting to you there is the idea that they are 95% confident that the sample that they took is no more than 0.03 percentage points away from the true population proportion. So let's move on to what I call the postscript, where we'll explore the meaning of confidence intervals. I've alluded to this in previous videos, but I've saved this here till last. What we're going to do is look at a spreadsheet that allows us to enter in some population proportion, a sample size, the confidence level that we're looking for, and then what the spreadsheet does is it randomly generates 100 sample proportions and then plots for us the 95% or whatever confidence interval that we specify. It plots 100 of those intervals here on this graph. So this red line right here represents the population proportion of 0.75. You can see that's very close here. And then each one of these orange bars is a single confidence interval that's generated from a random sample of this size based on this population proportion and this confidence interval. Now for this static image right here, you can see that this 100 sample proportions generated these 100 confidence intervals, and you can see up here it's reporting to us that 96 of them cover the true population proportion of 0.75. You can actually see there's 4 of them that don't work. So you can see there's one right here. This interval right here, which is way out over here on the right, does not cover this population proportion. There's another one down over here. You can see it down here. There's another one over here. That's the third one. And there's a fourth one here lurking somewhere. It looks like it's right here. Right? So 4 out of 100 do not cover, and therefore 96 out of 100, or 96% of them, cover the population proportion. So now I'm going to switch over to Excel and just sort of play with this a little bit so you can see. And you can download this particular Excel spreadsheet from the link that will appear here in a minute in the annotation. So let me go over to Excel here. This is a live version of this. I'm going to go back to the example where we had a population proportion of 0.6. We had a sample size of 85. I think this was the golfers example. We're going to construct a 95% confidence interval. And you can see here that for this particular set of 100 sample proportions, 93 of them cover the population proportion of 0.6. So you can see there's 7 of them. Here's one over here that doesn't cover the red line, so it's not covering the population proportion of 0.06. And you'll see others. There's another one down over here. And if you look carefully, you'll be able to count 7 of these. But I can actually do, I can randomly generate another 100 of them and see how close this gets to 95. So I'm going to go ahead and generate another 100. In that case, 94 of them cover the true sample proportion. If I do another one, there's another 94, 93 in that case, 93 again, 97. But what you can see if I do this over and over, if you pay attention very carefully to this cell that's right over here, you'll see that on average, the number of intervals that contains the population proportion is hovering around 95. So if I did this thousands and thousands of times, we're going to see that hit 95% due to the law of large numbers. So this is the idea behind a 95% confidence interval. If we were to generate 100 intervals from 100 samples, then on average, 95 of those intervals would contain or would cover the fixed sample proportion 0.6. Notice this proportion doesn't change. Like I've been saying before, this is fixed. This proportion is fixed. What's changing is all of these intervals as I draw new samples from that population. And I can change this to whatever population proportion I want. So let's say I'm looking at 0.51 is a population proportion. My sample size is maybe a little bit larger at 150 people. I'm still looking at a 95 confidence interval, and if I generate new intervals, you still see the number of intervals hovering on average at 95. If I switch the confidence interval to something smaller like 0.9, which is another confidence interval that sometimes is used, and generate sets of 100 sample proportions and intervals, you see here, in this case, 84 of them covered the proportion, 91, 92, and you can see now, due to the laws of probability and the theory that we've been talking about, you're going to see that average be around 90. So 90 of these intervals are going to cover that fixed population proportion of 0.51. So when we talk about a 95% confidence interval, that's what we're saying. We're basically communicating to the reader or the person to whom we're reporting our results that we are 90% confident that the sample proportion that we've come up with is going to actually contain the true population proportion. And the reason we say that we're 90% confident is because out of 100 sample proportions and 100 of those corresponding confidence intervals, on average, 90 of them, in this case 91 for this particular scenario here, on average, 90 of them are going to contain the population proportion, and therefore, we're 90% confident. So going back to our slide here, that basically wraps up this particular video. And so hopefully by now you have a good sense of what we mean by interval estimates. And in this video, we focused a little bit on sample sizes and then wrapped up with a quick discussion of a visualization of what we mean by 95% intervals or 90% intervals. So I hope the video was useful, and we will see you in the next video.